Okay, so we are ready to proceed with the next talk. I'm very excited to hear about the Magnon BECs in spin polarized atomic hydrogen gases. So we're switching from the solid state Magnon physics to actually hydrogen gas, and I'm very excited to welcome Kalle Antti Suominen. Sorry for that, but I'm very excited to have you and looking forward to your talk. Thank you.
Okay, thank you, Florian, and I want to thank the organizers for inviting me here. My topic is indeed, there are words like magnons and spins, which are familiar to you all, but maybe the physical system is something very different from the one that we heard from Christian Riedel just a few minutes ago. So indeed, I'm Kalle Antti Suominen. I come from University of Turku, which is about 150 kilometers west from here. Turku is the oldest city in Finland and actually the original site for University of Helsinki. And I start by mentioning my collaborators. So I'm a theoretician. So if you are going to ask questions about experiments, I may or may not be able to answer those. And pretty much all this experimental work has been done in the group of Sergei Vasiliev. They have a long history in atomic hydrogen research at Vihuri Physical Laboratory at our university. On theory side, Sergei is on the left in the picture. Then we have in the middle Lauri Lehtonen, who's been working on the theory together with Otto Vainio, who has already left for private industry. And in experiments there has been some collaboration also with David Lee and his group at Texas A&M University. So this may be a little bit sort of older work, but I chose this because it ties in well with the current topic of this workshop. So, quantum gases. The thing with these gases is that they don't become liquids or solids even when you go to zero temperature. That's a very important thing. And what you need is you typically operate with spin polarized atomic hydrogen. I explain soon what's that. And then deuterium is another possibility, but perhaps most famous are the alkali and alkaline earth atoms that have been cooled down to very low temperatures, and that's where you get very interesting physics. With bosons you get Bose-Einstein condensation, and with fermions you get all kinds of situations when you combine these with optical lattices. You may actually simulate many of the solid state phenomena. And indeed, recently people have been able to cool into Bose-Einstein condensation even diatomic molecules. That's quite an achievement considering how many different states you have in molecules. And these particles indeed, they can be considered as composite bosons or fermions. And that's why the spin is an important property. There are various cooling and trapping mechanisms for these gases, and especially the important thing, one reason why we need spin polarization is that you want to suppress the losses by collisions. You will have those losses, but if you suppress them sufficiently, you have time to do observations before your sample gets lost. And what is the motivation for this? Very much there is this thing about high precision measurements, and also looking for quantum sensors. One big topic has been atomic clocks, very accurate atomic clocks with these systems. And nowadays also you can do all sorts of quantum simulations with atoms trapped in optical lattices. And the basic quantities here is of course the particle density and then the mean distance in a gas between the particles. And you want to define some kind of a size for the particle itself. Let's call it R0 and de Broglie wavelength. And the thing is that the region we consider classical or thermal and sometimes called Maxwell-Boltzmann gas is the one where the mean distance between the particles is much bigger than the particle size, but the particle size is much bigger than de Broglie wavelength. Because de Broglie wavelength is the one which decides whether you are quantum or not. And indeed, quantum gas is something where the Broglie wavelength exceeds the particle size. And that's when you start to talk about whether these particles are bosons or fermions. But there are still two regimes here. One which has been studied very little, but I'm going to talk about that, is when the gas is still non-degenerate, it means that the Broglie wavelength is still less than the mean particle distance. If you want to go to these modern topics, Bose-Einstein condensation, fermionic behavior and such things, you have to go into degenerate quantum gas. And that's where the Broglie wavelength exceeds the mean particle distance. That's when the quantum effects really come into place. You have to use quantum statistics. But I'm going to talk about this non-degenerate quantum gas region. Now, if we have low densities and low temperatures, the only thing we have to consider is binary collisions pretty much, especially when talking about elastic, most frequent collisions. You can have three-body collisions, but they are typically a loss process. You want to avoid those. They will limit the lifetime of the sample. When you go there, in scattering theory, for bosons, you only have to worry about the S wave. And when you have S wave, basically everything is characterized by the scattering length. So you can replace actually this particle size with the scattering length. Notice that it can be either positive or negative. When you are looking especially degenerate gases, you notice that the negative scattering length corresponds to attractive forces. It's very difficult to keep that gas stable, whereas positive scattering length is a repulsive interaction, and that allows you to do Bose-Einstein condensation and many other things. Okay. Now, spin polarized atomic hydrogen. We have 4 hyperfine states, if we include the magnetic substates. Originally here we have the combined nuclear and electron spin, and we can have either F equal 0 or F equal 1 states. But I'm going to talk mostly about things happening at magnetic field values of several Teslas. And then you find that you have a very different state structure. You have the 2 states which are sort of high field seeking states, and these are the ones that one typically deals with. And you can see that this B state is doubly polarized. Electron and nuclear spin, they point at the same direction, and also the large B field means that nuclear spin and electron spin, they are more or less good quantum numbers. And that's very important here, because instead of having the sum of them, you can have them separately, and with NMR you can manipulate the nuclear spin, assuming electronic spin is frozen. But the same thing with electron spin resonance, you can manipulate the electron spin while thinking that the nuclear spin is frozen. So that allows to have some experimental freedom. Now, this A state is actually something that when you create the gas of hydrogen, you find that you get both A and B state, but because this is something that disappears collisionally very fast, you are left with a sample which is mostly only on B state. And that one is a long-living state. So, again, collisions, you can describe them with the molecular singlet or triplet potential. And the attractive singlet potential is indeed where you have the opposite spins, and this means that the atoms recombine into H2 very quickly and disappear. But doubly polarized ones, then you are dealing with triplet potential, and that's repulsive, so you don't have this problem. There's no bound states there. And you can have samples which live like 300 to 1000 seconds, so that's a long time to make experiments. Now, some numbers. When we are talking about low temperatures, then for me it's always something which is below 1 Kelvin. So we are dealing about something like 200 to 600 millikelvins. Densities in this experiment is between 10 to 17, 10 to 18. They are relatively high, but still the gas is considered to be dilute. B field is around 4.5. And now the important numbers. The scattering length is 0.072 nanometers. Particle mean distance is about 10 nanometers. But de Broglie wavelength, which is calculated by this thermal gas equation, that's about 3.2 nanometers. So we are in this quantum gas limit, but not at the degeneracy. That would require us to go 1 order of magnitude less in temperature. Actually, BEC was achieved with alkali atoms, rubidium and sodium and lithium as well, 30 years ago in 1995. Several decades, starting already in the 70s, people were trying to get Bose-Einstein condensation with atomic spin polarized hydrogen. But it's a difficult gas to deal with. So eventually then Dan Kleppner and his people at MIT got with the D state. So remember the spin polarized state, but the one which is high field seeking. So with that one, but you see, they got very low densities into the micro Kelvin region, but much so temperatures, but much smaller densities than what we have here. But still, for us to get into degeneracy would mean 10 orders, 1 order of magnitude in temperature. But this is not really the aim. I will tell hopefully later on how things are going then on experimental side nowadays. Okay, so the experimental setup. Those who are familiar with laser cooling or evaporative cooling and magnetic trapping or optical trapping, this setup which is the alkali or alkaline earth systems, this is a very different one. So basically cooling is done with liquid helium. And you end up creating the spin polarized, this is the sample volume, gas here, and they are compressing it by allowing this helium to go up and compress this cloud. Now, one of the most difficult things in this system is diagnostics. It's something what you can do is with magnetic fields or with this NMR and ESR fields. So here is like a half and Fabry-Perot cavity. This is fixed, and you actually build it so that there is an evanescent wave entering this sample volume. You can't tune this field here. It's this 128 gigahertz. But what you can do is that you have the magnetic field. So instead, you tune the atoms. For me, who has a background in laser physics, it was always a little bit difficult to think about this because you tune the atoms and not the field. But that's what it happens. And remember that these are spin polarized, so the field go in this direction up, but the polarization is down. And so basically this evanescent wave region is where we do the detections. And also this is the field you use to manipulate the spins. So basically it's just flipping the spin, which means that the spins get this component in the XY plane. And an interesting thing is that basically you have a homogeneous magnetic field here, but the surrounding epoxy has impurities, and they actually produce an additional field which is in this direction, but it alters a little bit this actual applied field, and that's important in some of these experiments. So now we get into an interesting phenomenon which requires identical particles happens, one of these few quantum things that you can get in a non-degenerate gas. So let's think just an elastic collision. They are identical particles, but the spins are slightly tilted compared to each other. And let's just assume that one of them is in a z direction and one of them is slightly tilted with the external field. And this tilted particle, this is the description for that as a wave function. So the interesting fact is that when this collides with the particle that has a spin up, for instance, then it's a collision between identical particles. When the collision is with this part of the wave function, it's actually an distinguishable particles. And this actually leads into different kind of scattering events. So, what is the final outcome of this process is that you have two spin components and they acquire different phase shifts. That's part of the story. This is the microscopic part. What actually is surprising here is that this effect is cumulative. When you keep having these collisions, you are acquiring bigger and bigger phase difference, and you are also then locking these different particles in your sample, and suddenly you have spin wave modes in the sample. These spin waves, because this is confined gas, they are typically standing waves. So you can expect a discrete spectrum there. Well, there has been a lot of theoretical studies on this from different angles, whether it's a molecular field or this kind of binary collisions. I would say that this article by David Lee is the best summary that I've found so far about this effect. Now, this has also been seen in liquid helium and spin polarized gases, or the theory has been done. Now, what turns out after all this collective phenomena is that the spin wave modes are described by a Schrödinger-like wave function for the magnetization. And you can identify here different terms. Spin diffusion is important because there's always spin diffusion. And in order to see these effects, they have to be stronger than the spin diffusion in the system. So, and luckily enough, especially if this mu character is very large, like here it is, you have to have a sufficiently large de Broglie wavelength, then this equation simplifies into something where this spin diffusion has a lower role. You can also define a dispersion relation out of this equation, which is a bit like this. But this term here is important because this contains variations in the field which is in the z direction. They will become important. Now, these have been studied already some time ago, and the nuclear spin waves were already observed by David Lee and his co-workers in 1980s. And they had a linear B field gradient appearing in the potential-like term, and the solution for that, you know, from a particle in a gravitational field as well, it's Airy functions. And they form a discrete spectrum, and indeed they found this kind of nuclear spin waves in their system. Okay. This is something we observed then, or the experimentalist observed in Turku. Remember that you can actually go and really write this equation in these terms, that you have the kinetic term and you have the potential. And indeed, when you have the gradient, you have the linear potential and you see the Airy functions here, and the spectrum shows them as well. And this matches with the theoretical calculations quite nicely. Okay. Now, what was actually then surprising, if you switch off this field gradient, you find this small inhomogeneous part in the field because of the epoxy. And actually it then concentrates on these parts on the side, and this is like a toroid or saddle or semi-toroid potential here. And indeed, this is something what it looks like if you have the Z and let's say X plane. This is the ground state. You can see it's localized here on the edge. But as you go into higher modes, you start to propagate between these two sides here as well, entering the center of this toroid. And what we can see is that there's the main peak for the ESR spectrum, but on the side, shifted there, is a peak, because there's a main peak. This looks like a dispersion here, what we interpreted as trapped Magnon. So we are seeing spin wave modes in this toroid. And if you actually shift the phase for the signal, this is what you see here. And what is interesting is that if you have low densities, it's a broad peak. And when you go higher densities, you get a sudden strong peak at the center. And this is actually something that we interpreted as Magnon BEC. Here is a similar results as well. But that was the toroid. Now, if you keep compressing this gas and you add again this gradient field, what happens is that this liquid helium actually passes the sides here, and you get a sphere of helium gas, or hydrogen gas. It quickly compresses, which means that it's not a very long living, but it has the advantage that while it compresses, the densities become very high. So, what happens when it compresses? Here is basically the Magnon spectrum again. On the spin waves on this spherical system. And at some point when you exceed the critical density, you get the peak. And this peak is now interpreted, you can call it spontaneous coherence, but you can also think this as a Magnon condensation. And let's take a little bit on Magnon theory. Well, they are bosons, like all quasi-particles typically, and they have no physical mass. So can they actually condense? Well, we have several physical systems nowadays where you have observed the condensation. So this kind of BEC-like behavior for massless quasi-particles. The first predictions for that were by Fröhlich, and then later on the theory has been developed. Now the catch here is that in thermal equilibrium, you would write down the normal Bose distribution. But for quasi-particles, the chemical potential here, unfortunately one uses mu here, and one for historical reasons also uses mu for another spin wave parameter. So chemical potential is 0 here, so it means that there will be no condensation as T goes to 0. However, we can go into a non-equilibrium system. We can have pumping in the system. And it turns out that if you have external pumping, like the ESR field in our system, it can induce a chemical potential, which is actually then proportional to the intensity of the pumping, then the ground state energy of the spin waves, and then 1 over temperature. And you keep changing Well, actually in our system, the condensation appears when the chemical potential and the ground state energy are equal. Now, which of these quantities is the changing one when the density changes? Actually, it turns out that this mu is independent of density. Okay. But this Magnon ground state energy actually decreases towards the mu as the density increases. So we approach mu from up, and at some point when they are equal, the condensation takes place. And here you can see the calculations for the Magnon ground state energy, whether we are in this toroidal trap or whether we are in this spherical situation here. You can see that the ground state energy goes down, and then you can see that these are the calculated sizes of the sharp peak. And you can see that at some density they emerge and they increase then very strongly, and especially for the spherical case, very quickly with the density. So this sort of shows that the experimental data is in agreement with this theory that has been derived. So maybe I have been too fast, but that makes chairperson always happy. But what I have told you is that indeed the spin waves in quantum gases is a true quantum phenomenon, and you can have that even when you are not in a quantum degenerate system, but the statistics play a role in collisions. Nuclear spin waves have been observed a long time ago, but we were the first ones to observe electron spin waves. And in addition, something which was not there with the nuclear spin experiments was that in fact we can see that the magnons occupy spontaneously and coherently the spin wave ground state. And we interpreted this as a non-equilibrium quasi-particle Bose-Einstein condensation. So that's the summary, but maybe a little bit about current status or the future. So experimentalists have already built a new experimental setup where you can also use laser light there for handling the particles or diagnostics. You can see that the wavelength for this laser is quite demanding, goes into ultraviolet very strongly. And this is a double trap with the idea that is that you first go into this, you can see we are already down to 1 millikelvin compared to this on the order of hundreds of millikelvins we had earlier. Density goes down, but the temperature goes down even faster in a way. And the aim is to go into microkelvin region. Remember, this was where the BEC was achieved, but density is then lower than what was, for instance, in the MIT experiment. But this is part of an international collaboration, and there are several topics to be studied. There's a quantum reflection on the superfluid helium. It's an interesting phenomenon. Perhaps something which is very fundamental is looking at gravitational quantum states. And here the idea is that in Turku they are making the studies with hydrogen, and at CERN making the same studies with anti-hydrogen. So what we are looking is whether there is some difference how gravitation treats particles and antiparticles. No signals about deviation yet, but this is a fish which is too important for not to catch it, even if it might be a fish that doesn't exist. Also then, if you want to test various beyond standard model theories, you take this one fundamental line in hydrogen, 1s, 2s line, you do spectroscopy with that with increasing accuracy. That's one important thing. And of course, then creating an optical clock in hydrogen. And something which came up very recently is atomic tritium. And there's now discussions about collaboration with people in Karlsruhe with the Katrin experiment, and also with similar experiments in US. You see, tritium, it's radioactive. It's about 12 years of half-life, which is okay, it's not very active. When it decays, one neutron turns into a proton, which means that you get an helium ion. You get one electron out, so you get beta radiation, and you get one neutrino. So if you can detect the electron and helium very precisely, energy and momentum, you can actually then deduce what you have in neutrino. And that's why they have these huge experiments ongoing. But so far they have used molecular tritium, tritium-2. But it would be, if you want to go to higher accuracy, to use atomic tritium. And then all these experimental tools are applicable to tritium atoms as well. So this is something which is new and hopefully starts a new branch of research, but then perhaps going into more fundamental things rather than looking at these quantum gases. So that's all I wanted to say, and hello to all experimentalists from Turku if you are online, and thank you very much.
Thank you so much for this very nice perspective from a slightly different angle. Do we have questions? We have one question. Maybe in the meantime, I'll ask, you mentioned the spin diffusion and its omnipresence. Yeah. And I saw, if I read the equations right, it's driven by a spatial density gradient.
Actually, in these experiments, the density is basically it's homogeneous over the sample. So there's no density gradient. The density changes especially when you are compressing the gas, but there's no density variations that would play a role.
So where is this spin diffusion coming from then?
I think this is something which you normally have for thermal gases. So this is about, you know,
just
elastic collisions. Yeah, something like that. So it's just a normal, I would say it's a normal thing. And then the behavior I showed is something which is purely quantum, and it has to be very strong to be observable.
I understand. Okay, but now I get it. Well, we have a question.
Thank you. Very nice talk. I didn't quite catch why the spin wave energy changes with density. I thought it's defined by the magnetic field gradient. But somehow you are saying that when you increase the density, the energy of your magnons goes down.
Yes, that's because what you do, you take the geometry. You take the equation for spin waves, and then you calculate from that. And in this particular case, where you, for instance, a shrinking bubble, you are changing the system. I didn't show you all the derivations, but basically it's actually surprising that the chemical potential doesn't depend on density, because you have density dependent terms there, but suddenly they cancel each other. And then you are left with this ground state energy, and that changes with the density. So.
Thanks.
If we have time for...
Thanks for a nice talk. I have a bit technical question first. You, on the very last slide, you mentioned this 243 nanometer laser.
Yeah.
This is supposed to be used for cooling, or?
Now let
is
me
it what
think.
you need to cool the atom?
Yes, it's supposed to be used for, I think, both for cooling or detection as well.
Okay. I was just wondering, because hydrogen is very light gas. Do you expect some issues with the photon recoil? Because it's going to be quite strong here, right? So the kick provided by a photon to an atom is insane, I guess.
Yeah, well, no, I'm not certain, but what I'm looking at microkelvins, and the recoil kicks are usually on, I think, on a lower level still, so they are not that. But I'm not the experimentalist here, so.
Right.
But that's my gut feeling about this, that it's not yet playing a role.
And maybe a little broader question. You want to get a Magnon BEC on top of the atomic BEC, is that correct?
No.
Huh?
No. So, like I said, we did this Magnon study some time ago,
Yeah.
and already then decided not to try to go to
Okay.
BEC. And then gears shifted completely into a
Right.
new setup with new aims. So, two different worlds.
It's a closed chapter, yeah? Okay.
Yeah.
Thanks.
For now, but who knows?
So, with that, I would like to close the session and send us all off to our coffee break. Let's thank the speakers of the session again.